Good day students. Myself Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. Students, we were discussing the paper Solid State Physics. This is the fifth paper of MSc Final Physics. In this, we were discussing ferromagnetism. In our today's lecture, the topic will be domain theory of ferromagnetic substances. This domain theory was proposed for ferromagnetic materials by Weiss. According to Weiss, a ferromagnetic material can be divided into small number of regions which are called domains. For example, here I am showing a ferromagnetic material and we can see clearly that it is divided into small regions, and each of this small region it is termed as domain, and these domains are magnetized spontaneously. The size of the domain, it can vary from 10 raised to power minus 6 to the entire volume of the crystal. That means that in a ferromagnetic material there can be a number of domains, a large number of domains, or we can also have a ferromagnetic material which is having a single domain, so that this single domain occupy the entire volume of the crystal. We can see that in this ferromagnetic material the magnetization is there in every domain, but the direction of magnetization in every domain is different. This direction of magnetization is random in all the domains. Hence, the spin moment of atoms in a domain, they are oriented in a particular direction, and when there is no magnetic field applied to the specimen, then the magnetization of the different domains, which is random, they give us the resultant magnetization to be 0. The resultant magnetization can be obtained by the vector sum of magnetization of individual domain. And the random orientation of these domains occur in such a way that resultant gives us 0. Now, if we apply a magnetic field along the surface of this ferromagnetic material, for example, I am applying magnetic field parallel to the surface of ferromagnetic material, then here as we can see, the magnetization moment alignment of individual domains change. They tend to align themselves in a direction parallel to the external magnetic field. So this shows the behavior of a ferromagnetic material when an external magnetic field is applied. Hence we can say in an demagnetic material we can induce ferromagnetism by the application of external magnetic field. All these domains, they rotate and orient themselves in the direction of external magnetic field. So it is evident from this diagram that initially we have a ferromagnetic material which is in the demagnetized state, and we have small domains in it. These domains are spontaneously magnetized, and the spontaneous magnetization is in such a way that they add up to give a net magnetic moment to be 0. But here, when external magnetic field is applied, then these magnetic moments they align themselves in the direction of external magnetic field, so that a magnetization is developed in this ferromagnetic material. Now, here I am showing domain in a single crystal of iron. The first figure, that is this A figure, shows that we have a ferromagnetic crystal and we have divided it into domains. And this domain structure varies on application of magnetic field. In this second figure, a weak magnetic field is applied. This shows weak magnetic field. Then we can see that these domains walls they shift so as to align themselves in the direction of magnetic field. Now what I am doing further, I am changing my magnetic field. When strong magnetic fields are applied, then it is clear from figure that these domains change the direction of magnetization. Earlier in the demagnetized state, this was the direction of magnetization. Now application of strong magnetic field rotates the direction of magnetization. This was earlier when there was no magnetic field, and this is the direction on application of strong magnetic field. By further increasing the magnetic field, it is clearly evident from the figure that domains have magnetization which are parallel to the direction of external applied field. All the domains have set in such a way that magnetization is in the direction of external applied field. Now, here we can see if the external field is still removed, that means we are removing any external source which produces a magnetic field. Then the direction of magnetization persists in this domain even when external magnetic field is 0. That means now our specimen has a permanent magnetic dipole moment. That means it has become a magnet. This is the base of existence of permanent magnet. And this phenomena which produces a permanent magnetization in a demagnetized material is termed as magnetic remnants or magnetic retentivity. It is clear from this figure that earlier we have a ferromagnetic material which have domains, they are oriented in random direction, and by the application of strong magnetic field, the random direction of domains change in such a way that now they are parallel to the external magnetic field. So we have changed our material from a demagnetized state to a magnetized state, and which will remain even after the removal of external magnetic field. Now here we have shown a ferromagnetic material in which there is a single domain. These are the two poles of this magnetic material. This show the direction of magnetic lines of force. Now, we have divided our ferromagnetic material into two domains. These are the two domains of our ferromagnetic material, and the magnetic line spread is also shown. What we are doing? We are further dividing our ferromagnetic material into a large number of domains. This shows the further division of a ferromagnetic material. On comparing these three diagrams, we can see that the field is going to reduce continuously. Earlier, the field line spread was large as compared to the second diagram, and when we compare second and third diagram, then we can see that in the third diagram, the field lines spread is very less as compared to second and as compared to first figure. We can say that energy reduction comes from surface poles, as we can see that the area reduces very small. Now, when we have to divide a ferromagnetic material into domains, how long this subdivision process should continue? When we are dividing our ferromagnetic material into domains, there will be a decrease in field energy, but there is an increase in Heisenberg exchange energy, because more and more magnetic moments are aligning antiparallel. Here we can see by division antiparallel alignment has been induced. On further subdivision, antiparallel alignment increases more. Finally, a state will be reached in which further subdivision will cause a great increase in exchange in energy than decrease in field energy, and the ferromagnet will assume a state of minimum total energy. That means this subdivision of a ferromagnetic material into domain, this should continue until a state of minimum energy is reached. That state will be the stable state for a ferromagnetic material to be achieved. So, in our today's lecture, we have shown that a ferromagnetic material is made up of small number of regions, and these regions, they are spontaneously magnetized, and the magnetization direction in each domain is random. There is no particular direction, but when an external magnetic field is applied, then in such a case, domains tend to align themselves in the direction parallel to the externally applied magnetic field. So, in this type of material, a magnetic field will be induced. Thanks a lot for watching.